Sorbonne University. And Michel is a very well-known figure in Indian mathematics, not only India, all over the world. He's an expert in so-called transcendental number theory all over the world. In fact, he's a pioneering figure into that area, but not only that area, he works in many other areas. And of course, he's one of the pillars of modern mathematics in number theory especially, but he's also very active in popularizing mathematics into the places where we dare not go. Like even in the very interior places in Africa and many other places, Michel go there and it is too simple and too easy a thing. So it's a wonderful location, Michel. Thank you so much for accepting our offer. And right now we are all eager to hear you. Michel Waldschmidt.
Okay, thank you very much. So do you see my screen?
Yeah.
Okay, thank you. Do you see my screen?
Yeah, it's visible, fine.
Okay. So I am very thankful to the organizers and especially to Kalyan for this invitation to give a talk in this conference. And I take this opportunity to congratulate Kalyan for being the new director of the Kerala School of Mathematics. It is a superb institute that I visited several times, and I like very much the place. I am very sorry that I cannot be with you physically, but I am glad that I can participate to this conference. So I chose a topic which is integer valued entire functions. I am sorry that I am not going to quote Ramanujan, apart from just now when I mentioned his name. But I want to discuss this topic because it's an old topic which has some close connection with some recent work. And so I thought that it may be good that I give some survey on this topic. So what is the title? What is an integer valued entire function? It is an entire function, which means an analytic function in the plane, which takes integer values at the non-negative integers. And a fundamental example is 2 power z. I will speak also of Hurwitz functions. Instead of taking the values at the non-negative integers, we take the derivatives at one point, for example, 0, and we ask that all the derivatives are integers. And an example is exponential of z. And so the main purpose is to give low bound for the growth of such functions and similar ones when they are not polynomials. And I will start by explaining the connection with my favorite topic, which is transcendental number theory. So I will explain the connection between integer valued function and transcendental number theory. Then I will review the subject of integer valued entire function. And after that, I will present some new results which are related with the Lidstone, Whittaker, Poritsky, and Goncharov interpolation. I can tell you that I was interested with the Lidstone interpolation 2 years ago when I participated to the conference on special functions. I gave a talk there, and then I was the chairperson of a session of a talk by M.A. Patan. And in fact, I was invited to this conference thanks to Kalyan. And so when I was the chairperson of the talk by Patan, I listened very carefully, and he started by speaking of Lidstone interpolation. I had no idea of what it was, but immediately I realized that there was a connection with integer valued functions. So I will tell you what I did after these 2 years. So I start with the connection with Hilbert-Stevens problem and transcendental number theory. Among the 23 problems of Hilbert in 1900, the 7th was to prove that the numbers exponential of pi and 2 power square root of 2 are transcendental numbers, which means that these numbers are not algebraic, they are not root of a polynomial with rational coefficient. So these 2 numbers are values of the exponential function. 2 power square root of 2 is the value of the exponential function at the point square root of 2 times log 2. And the exponential function takes some values which are rational, like exponential of 2, which is 2, and exponential I pi, which is -1. The function takes also transcendental values, like e, the exponential of 1. And so the question is to predict when a value will be algebraic or transcendental. Here it is the value of the exponential function at a transcendental point, and it can be algebraic and it can be rational or it can be transcendental. So it's not obvious to answer the question. When Hilbert asked his question, it was known that the number e itself, the exponential of 1, is a transcendental number. This is a very fundamental work of Hermite, which really started all the theory of transcendental numbers, and a very large percentage number of proofs of transcendence nowadays are based on Hermite's work and Hermite's construction and Hermite's formulae and so on. So this was more or less the state of the art at this time. It was known by Lindemann that exponential of alpha is transcendental when alpha is algebraic. And this is the Hermite-Lindemann theorem, and Lindemann proved the transcendence of pi. But for e to the pi, it was not known. In her book on Hilbert, Constance Reid wrote the following. There was a lecture by Karl Ludwig Siegel in Göttingen. It was a lecture by Hilbert, and Karl Ludwig Siegel was a student at that time in Göttingen. And Siegel attended the talk by Hilbert. And Hilbert mentioned 3 open problems in number theory. The first one was the Riemann hypothesis. The second was Fermat's last theorem. And the third was the transcendence of 2 power square root of 2. And Hilbert said that given the recent progress, he hoped to see the proof of the Riemann hypothesis in his lifetime. He said that Fermat's problem required a totally new method, and possibly the youngest member of the audience would live to see it solved. As for 2 to the power square root of 2, Hilbert said that no one at the lecture would live to see the proof. So it was more or less the opposite which occurred. The youngest member of the audience was Siegel, probably one of the youngest, and Hilbert contributed to the solution of the Hilbert seventh problem and to the transcendence of 2 power square root of 2. For Fermat's problem, the solution was given once everybody of the audience in this lecture passed away. And as you know, for the Riemann hypothesis, we are still waiting. So the solution of the problem of Hilbert came in 1929 and 1934, and it came from a way which was rather unexpected. It was from the work of Polya on the growth of integer-valued entire functions. Polya studied the situation for the integers, and Gelfand extended it to the integers of the Gaussian field, which are the elements of Z of I. You see, it looks like an exercise for a student if something is true for the integers to see whether it's true for Z of I and whether the same proof works. And this was the case with this work of Gelfand. So what Polya had proved for the integers is the following. An entire function f, which is not a polynomial, and which satisfies f of a is an integer for all non-negative integers a, grows at least like 2 power z. So what does it mean that it grows like 2 to the power z? The result of Polya, the first result of Polya was that the lim sup of 1 over r log fr is at least log 2. So fr cannot be exponential of alpha r, where alpha is less than log 2. This fr means the sup of f of z on the disk of radius r and center 0, and it is the same as the sup of f on the boundary of the disk by the maximum modulus principle. So this is the initial result of Polya. I will come back to this statement because this is the first main result in the field. And what Gelfand did after some work by Fukasawa is to extend this result using the same proof to functions which take integer values in Z of I. So for all the Gaussian integers are a plus ib, we assume that f of a plus ib is in Z of I, and it is an integer in the sense that it is Gaussian integers. And what Fukasov and Gelfand proved is that such a function grows at least like the exponential of z square. So it's not exponential growth, it's the square of z in the exponential. And the precise result is that the limb sweep of 1 over r square log fr is at least some positive constant. And the constant which was found by Gelfand was strictly positive, but it is the lower bound is 10 to the minus 45. So it is a very small lower bound. And the proof is essentially the same as for Polya, which is to expand f of z into a Newton interpolation series at the Gaussian integers. So this constant gamma is the right value for the following reason. If you take the canonical product associated with the lattice z plus zi, this canonical product is the Weierstrass sigma function, which has this expansion here. It is an entire function which vanishes on z of I, so it's more than to have integer values. It is 0. And it grows like exponential, a constant times z square. And this constant is pi over 2. So the value of the constant gamma found by Gelfand, we know that it is at least 10 to the minus 45, but it cannot be more than pi over 2. The value of this constant is something which was open for a long time, and it was solved only by François Gramin in 1981, after David Masser gave an upper bound with pi over 2e. And so this result is the best possible one, and it solves completely the problem. So this is the result of Gelfand, but what is the connection with Hilbert's problem? I will explain the connection as follows. Consider the function exponential of pi z. It's a function which grows like exponential constant times z, which means that it is of exponential growth and what we say finite exponential type. So it does not grow like exponential z square. So it's not possible that such a function would take integer values at all the integers. But if you take a number of the form a plus ib in z of I, a and b are just natural integers, then the value of this function is a number which belongs to the field Q of exponential of pi. If the number of exponential of pi were a rational number, all these values would be rational numbers. So it's not exactly an integer value function, it's a rational valued function, but you see that it's not so far from the problem of Hilbert on the transcendence or even irrationality of exponential of pi. And if you take just the proof of Gelfand, you get the irrationality of pi, and in fact, you can get the fact that exponential of pi is not a root of a polynomial x power n minus a, where n and a are integers, n is greater than or equal to 1, and a is even a rational number. But in fact, the proof gives more if you twist it a little bit, and this is what Gelfand did in 1929. He proved that exponential of pi is a transcendental number. So this was really the first partial answer to Hilbert's seventh problem, 29 years after Hilbert asked it. Gelfand went a little bit further and proved that if you take for alpha a non-zero algebraic number where log alpha is non-zero, you choose a logarithm which is non-zero. So if alpha is equal to 1, you can take log alpha equal I pi, and or 2 I pi. And for beta, an imaginary quadratic number, then alpha power beta, which is by definition exponential beta log alpha, is a transcendental number. And this gives the transcendence of exponential of pi. So the result of Gelfand in 1929 works for imaginary quadratic numbers, and Kusmin extended this result to 2 power square root of 2, and more generally for the exponent beta, which is a real quadratic number. So the two numbers which I mentioned before, exponential of pi and 2 power square root of 2, were proved to be transcendental in 1930. And the general case came 4 years later, but the general case was not based on the same method, which is an interpolation method. It was based on a method which was introduced by Siegel using an auxiliary function. And the result is the full solution of Hilbert's seventh problem, the number alpha to the beta is transcendental when alpha and beta are algebraic numbers. Beta is an irrational number and log alpha is non-zero. And it is the same as to say that if you take two logarithms of algebraic numbers, the quotient log alpha 1 divided by log alpha 2 is either rational or transcendental. It cannot be algebraic irrational. So this is the connection which I wanted to point out between integer valued functions and the transcendental number theory. There are further connections which were developed by Strauss in 1950. He got another connection and got some general results which give the Hermite-Lindemann theorem on the transcendence of exponential of alpha. But in the footnote in this paper, Strauss explained that Schneider obtained more far-reaching results. And in fact, later it became the Schneider-Lang criterion. But I will not give more information on that line. I want to come back to my main topic, which is integer-valued entire functions. So an integer-valued entire function, as I mentioned before, is an analytic function in C, which takes integer values for the non-negative integers. If you look at polynomials, which are integer-valued, we know some of them, which are the so-called binomial polynomials, z minus 1, z minus n plus 1 over n factorial. These polynomials are integer-valued. If you take for z positive integer, then it gives an integer valued. And this set of polynomials gives a basis for the z module of polynomials taking integer values at the integers. So any such polynomial is a linear combination of the fundamental ones. We have a basis. What Polya proved in 1915, the result which I mentioned, is that 2 power z, which is exponential z log 2, which is defined like this, is the smallest transcendental integer valued entire function. The exponential type is 0.693 and so on. So it grows like exponential log 2 z, and you cannot get a smaller type, exponential type. The proof of Polya starts by expanding the function f into a Newton interpolation series at the point 0, 1, 2, and so on. So he expands this function as sum of un zn, and un is given by this formula in terms of the values of f at the integers. So if f of n is an integer, then un is also an integer. And the proof of Polya consists in showing that if net f does not grow too fast, then un, this absolute value of un, is less than 1, and therefore un is 0 for n sufficiently large, and consequently f is a polynomial. I will give a little bit more detail for the proof by using Laplace transform. So the proof can be done in the following way. You start from exponential of capital NT, where n is an integer, and you write exponential capital NT as exponential of NT minus 1 plus 1. And then you expand the exponential t minus 1 to the n by using this formula, which is just elementary. You just expand this in the binomial formula. And you look at what happens if t is less than log 2, which is just the bound given by Polya. Then this coefficient exponential of t minus 1 to the n tends to 0 geometrically because exponential of t minus 1 is less than 1. And therefore, the series, if you replace capital N, this one by infinity, and here you put z, you see that this function, the difference between the two sides takes 0 values at the integers, 0, 1, 2, and so on. So using the Laplace transform, we have replaced the fact that we have a function which takes integer values by a function which takes 0 values. And so we have a function which is 0 at all the integers. And there is a classical theorem in complex analysis of Carlson, which states that if an entire function of exponential type less than pi vanishes at all the integers, then this function is 0. So we get the result that the exponential of tz satisfies the desired result. But now if you take an entire function of exponential type less than log 2, you consider the Laplace transform of f, which is f of z is equal to the integral of exponential tz f of t dt. This is the inverse Laplace transform. And so f of z is given by this integral. And then you deduce that the un, which are these coefficients here, are given by this integral using just the inverse Laplace transform. And therefore, if you take a number r, which is between the type of f and log 2, you have an integral giving the value of these coefficients un. And from this integral, you deduce that un is less than 1. And therefore, if un is an integer, then for n sufficiently large, un is equal to 0. Okay, so this is the sketch of the proof using the Laplace transform. And we can go a little bit further using Laplace transform. I will explain it how. The result of Polya was a little bit sharper than what I said. It's not only that the exponential type is less than log 2, it is that if f is a transcendental integer valued entire function, so if f is transcendental, then this limit sup is positive. Or if you prefer, if the lim sup is 0, then f is a polynomial. So you see that it's sharper because you have 2 to the minus r, but you have a residue term, an error term, if you like, which is the square root of r. I mentioned the result of Carlson before, which is that an entire function of exponential type less than pi, which vanishes at 0, is 0. And this is best possible because of the function sine of pi z. And for Polya, it is, instead of pi, it is log 2, but instead of 0, it is values in z. So there is a strong connection, and we will see it again, between looking at integer values or looking at zero values. The result of Polya was refined by Hardy in 1917. Hardy proved that if f is an integer valued entire function such that the lim sup of 2 to the minus r, fr, is 0, then f is a polynomial. So you see it's better because you do not have the square root of r, which is here. So the assumption is weaker. And of course, for the function 2 to the z, the lim sup is 1. So it's not a contradiction. You could think that this is the end of the story because it looks essentially best possible. But Selberg went further. Selberg proved that if an integer valued entire function f has a type which is less than log 2 plus 1 over 1500, then f is of the form p0 plus p1 of z2 to the z, where p0 and p1 are polynomial. I am especially interested with the fact that the function satisfying this condition are countably many such functions. So with the exponential type log 2, you just have essentially 2 to the z, or a polynomial times 2 to the z plus p0. But you have only countably many such functions if you take a type which is just a little bit larger than log 2. Again, this is not the end of the story. Piso went further because what Piso proved is that if an integer valued function f of exponential type less than 0.8, and so it is an integer valued function, then it is a polynomial plus 2 to the z times a polynomial plus gamma to the z p2 plus gamma bar to the z p3, and gamma gamma bar are the non-real roots of the polynomial z cubed minus 3z plus 3. And Piso went a little bit further because he even succeeded to get the result for the exponential type less than 0.9934. So I will not go further for the subject of integer valued functions, but I will consider some similar problems, and I will consider several of them. And the first one is the topic of completely integer valued entire functions. So the definition is the following. A completely integer valued entire function is an entire function which takes values in z at all points in z. We have seen before the work of Gelfand, which was z of I. So Z of I is not really the analog of Z. It is rather, well, it is not the analog of N. It is the analog of Z. So it's quite natural to look at Z instead of N. And to give an example of a completely integer valued entire function, I will take the case where you start with a quadratic unit. So a quadratic unit will be a root of a polynomial x squared plus ax plus or minus 1. But I restrict here to plus 1. So I take a quadratic unit and I consider the function u to the z plus u to the minus z and u to the z minus u to the minus z divided by u minus 1. These two functions are completely integer valued entire functions of exponential type log u. U is greater than 1. And if you look how this function grows, when you look at the modulus of z, you have to look at the exponential modulus of z, real part of u, and the real part of u is u, because u is greater than 1. So log of u is the real part of the logarithm of modulus of u. So an example of quadratic units are the roots of the polynomial x squared minus 3x plus 1, and the roots are 3 plus or minus square root of 5 divided by 2. So we have an example of a completely integer valued entire function. Of course, you can take sine of pi z, but sine of pi z grows much faster. And now I have a quiz for you. Consider the golden ratio, which is the root of x squared minus x minus 1, which is greater than 1, and look at the other root, which turns out to be minus 1 over phi. If you take any integer n in z, positive or negative, you check in the same way that phi n plus phi tilde to the n is an integer. Now, if you look at the logarithm of phi, which is the same as minus the logarithm of phi tilde, this is less than log 2. So you have a function which is an integer valued entire function. It's a completely integer valued entire function. And you see that log phi is less than log 2. But Polya said that there is no such function of type which is less than log 2. So why is this function not a counterexample to Polya's result on the growth of transcendental integer valued entire function? So at the end of my talk, I hope there will be some questions, and I hope there will be an answer to this quiz, and you will tell me why it is not a counterexample. But now let me continue. I mentioned the fact that this function is a completely integer valued entire transcendental entire function, and Carlson, the same as the one for the zeros of entire function of type less than pi, proved that if the type of a completely integer valued entire function satisfies tau of f less than the logarithm of this number, which is 0.962, then f is a polynomial. Zellberg went a little bit further, like he did for the case of Polya and Hardy. Zellberg proved that if the type is less than this, the same number plus small epsilon, 2 divided by 10 to the 6, then f is of the form p0 plus p1, that this number to the z, plus p2 times this number to the minus z. And p0, p1, p2 are polynomials. It's easy to see that there are polynomials with algebraic coefficients, so you have only countably many such functions. Okay, so I will not go further for the values at the integers, positive or negative. And now I will start with another topic, which is similar, but which is related, but it's different. Instead of taking the values at the integers, I take the derivatives at 0. In this case, we speak of Hurwitz functions. A Hurwitz function is an entire function so that all the derivatives at 0 are in z for all n greater than or equal to 0. So for integer valued function, I explained that the binomial coefficients functions give a basis of the space of polynomials. Here, a basis of the space of polynomials which are Hurwitz function is given by the polynomials z power n divided by n factorial. And any polynomial which is a Hurwitz function is a finite linear combination of this with integer coefficients. Now, if you want a transcendental function, which is a Hurwitz function, the simplest one is the exponential function, which is the infinite sum of Zn over n factorial. So it is a transcendental Hurwitz function, and the exponential type is 1. If you take an integer a, the function exponential az is also a Hurwitz function, and the exponential type is the absolute value of a. So Kakeya, 1 year after Polya worked on integer valued integer functions, he did the same for Hurwitz function, and he proved that if a Hurwitz function has an exponential type less than 1, then it is a polynomial. And the precise result of Kakeya was that if the lim sup of square root of r exponential minus r fr is equal to 0, then f is a polynomial. You see, if you remember, there was a square root of r in the Polya assumption, and this square root of r was removed by Hardy. And so it is rather natural to ask, is this square root of r superfluous or not? The next step on Hurwitz function was done by Polya himself. But Polya did not remove the square root of r. What he did is to improve the assumption. Instead of writing equals 0, Polya refined Kakeya's result, a Hurwitz function satisfying the lim sup of square root of r exponential minus r fr less than 1 over square root of 2 pi is a polynomial. So he has this upper bound instead of lim sup equals 0. But Polya pointed out that this is best possible. So the square root of r here cannot be removed. And an example of this is given by taking a lacunary series. Instead of taking 1 over n factorial, you take a coefficient which is 0, 1, or minus 1, but there are very few coefficients which are not 0. So you take en, which is in 1 or minus 1, and you take en divided by 2 to the n factorial, z power 2 to the n. And this function, it's an exercise to prove that this function satisfies the condition that the lim sup is equal to 1 over square root of 2 pi. And you have uncountably many such functions. So the situation is very different from the situation of integer valued entire function. First, because you cannot remove the square root of r. And secondly, because when you reach the type 1, well, the limit 1 over square root of 2 pi, now you have uncountably many functions instead of countably many. I would like to state a result. I will not give the proof, but the proof is not too difficult, which is a variant of Polya's result. And the proof of the variant uses Cauchy's inequalities and Stirling formula. I will give a reference to the proof at the end of my talk. So the variant is the following. I will use it later. You take an entire function f. You assume that a is greater than or equal to 0, and that the lim sup of exponential minus r square root of r fr is less than exponential minus a divided by square root of 2 pi. You can take a equals 0, you have 1 over square root of 2 pi, which was the case of Polya. So the difference is that here we put exponential minus a. And the result is that there exists a n0, which depends on a and f, such that for n greater than or equal to n0, and for all z in the disk modulo z less than a, we have fn of z less than 1. And so the connection with Polya is that if fn of z is an integer for some values of n, then this value has to be 0. We replace integer values by 0. And this is very convenient. So I will come back to this variant of Polya's result later. We know more about integer valued entire functions. We cannot go further than the lim sup of square root of r exponential minus r fr less than 1 over square root of 2 pi. But Sato and Strauss gave some very sharp results where if you put the assumption that the lim sup of this with 1 plus epsilon over 24r minus 1 is less than 1, then there exists transcendental function. But if you take a Hurwitz function, then if you took the minus here instead of the plus, then if the lim sup is less than or equal to 1, it is a polynomial. Here you have plus, but you have the exponent -1. This explains why you need to have plus here and minus here. So this is extremely sharp, and it's a nice result of Sato and Strauss. I mentioned before Strauss, he contributed a lot to this topic. So we have seen integer valued function, and I use the following picture. I put the integers horizontally. We have seen Hurwitz function, and in this picture, I put the derivative vertically. And so I want to generalize integer valued function and Hurwitz function. How to do that? There are several ways to do that, and I will give several ways. The first one is horizontal, the second one is vertical, and we will see other ways later. The two first natural ways of mixing integer valued function and Hurwitz function is horizontal. We include finitely many derivatives, and we speak of k times integer valued function. Instead of taking one, if we taking all the integers with the value itself, we can take one derivative, two derivatives, or finitely many derivatives. And we can do it vertically. We take finitely many points, and we take all the derivatives. So this will be a k-point Hurwitz function. It is an entire function having all the derivatives at the first integers, 0, 1, k minus 1, which are integer values. We could speak of, we could take other points, S0, S1, Sk minus 1, but I insist that we take the integers, 0, 1, k minus 1. Okay, so let us look first at k times integer valued functions, which is horizontal. So this is the picture for k equal to. You take the values of f at the integers, and you take the values at of the derivative at the same integers. And this was investigated by Gelfond in 1929, the same Gelfond who finally solved the Hilbert's seventh problem. And Gelfond proved that the k times integer valued function of exponential type less than k times some logarithm is a polynomial. So you see the condition here is on the exponential type k. And the example of the function sine of pi z to the power k, which has exponential type k pi and vanishes with multiplicity k, show that this is not far from the best possible. But we do not have yet a complete picture of what is going on for k times integer valued functions. So this is horizontal. We take just two, the value and the derivative. Vertically, we have 2-point Hurwitz functions and k-point Hurwitz function. So let me start with k equal to. We ask that the derivative at 0 and 1 are integers. So this is the picture. We take all the derivative at 0, all the derivatives at 1. And Sato proved that every 2-point Hurwitz entire function for which there exists a positive constant c such that f is bounded by c exponential of r squared minus r minus log r is a polynomial. So you see that now it is the order of the function which comes into the picture, exponential r squared. And Sato proved that there exists transcendental 2-point Hurwitz entire function which grows almost like this. It is exponential r squared plus r minus log r. So this is rather satisfactory. But for k at least 3, we do not know so well. We just know that we do not have a result for the type, which is here we have just r squared and r squared without constant. But for k-point Hurwitz function, we just know by Sato that the order of a k-point Hurwitz function is at least k, which means that such a function, so you have k points and you go with all the derivatives, such a function grows at least like exponential z to the k. And you have an example here, exponential of z, z minus 1, z minus k plus 1, which has order k. The exponent is a power polynomial of degree k. And so this is best possible. Now for k-point Hurwitz function, we can define the type. If you take rho equal 1, this is the exponential type. If you take rho any positive number, for an entire function of order at most rho, we define the type of index rho as the lim sup of log fr divided by r to the rho. So the exponential type is tau 1 of f. And it means that f grows like exponential tau z to the rho. And if you take the function which I mentioned just before, exponential z, z minus 1, z minus k plus 1, the order is k and the type is 1. It grows like exponential 1 times z to the k. There is a claim by Bieberbach that if an entire function which is transcendental of order rho is a k-point Hurwitz entire function, then either the order is at least k, the order rho is at least k, or if rho equal k, the type is at least 1. So this would be the natural generalization of the result for k equal 2, which I mentioned just before by Sato. This is true for k equal 2, but Bieberbach claimed that it is true for any value of k. And it turned out that this result is wrong. It's rather rare in such a topic that people claim something which turns out to be wrong. Most often the claims are difficult to prove, but they are reasonable, but this was not the case. And the counterexample is an interesting one. You look at the polynomial 1/2 of z, z minus 1, z minus 2, z minus 3. And you look at the function exponential a of z. So if you take the values of this function and the derivatives at 0, 1, 2, 3, you find that these are integers. The fact that the derivatives are integers comes from the following remark. When you take the derivative, you have a of z, which is 1/2 of z4 plus 3z cubed plus 11 over 2 z squared minus 3z. And you see that the rational numbers have a denominator which is just 2, but they occur with an exponent of z which is even. And therefore, the derivative of a is a polynomial with integer coefficients. And this is sufficient to prove that this is a 4-point Hurwitz function of order 4, and the type is 1/2. So the situation is not clear. We do not know what is the truth. I come to another way of generalizing integer valued function and Hurwitz function, which is to introduce utterly integer valued entire functions. We assume that all the derivatives at all the points are in z. So the picture is like this. We have all the black points. Strauss suggested that maybe they do not exist. And Friedman in 1968 showed that there exists transcendental utterly entire function, but now they are not of finite order. They grow like exponential of z. The lim sup of log fr is less than r, divided by r is less than pi, and there exists some of them for which this same lim sup is at least log of 1 plus 1 over e. So they are double exponential. And the bound log 1 plus 1 over e was improved by Welter in 2005 to log 2. But there is still a gap between log 2 and pi. So we do not know the final result. I would like to give some example of Sato because it was expected by Strauss that they do not exist. And Sato found some examples which are rather easy to explain. It takes a series which is sum of an sine of 2 pi z with the power n. And it takes for an some integers which are suitably which satisfy this growth condition. And then he proved that you get a non-enumerable set of utterly integer valued entire function. And finally, there is another way of generalizing, of mixing the horizontal and vertical way, which is to take a diagonal way. And this was done by Abel, who studied the values of functions, entire functions, so that the derivative of order n at the point n is in z. So Abel, it was an early work of Abel, which he did not publish, but which was published after he passed away, after 1829. And so he studied this function, and he introduced the so-called Abel polynomials, which are the polynomials Pn equal 1 over n factorial z minus n to the power n minus 1. They are very interesting polynomials because if you look at the derivative of order n of Pn at the point n, it is 1. And if you take the derivative of order k of Pn at the point k, then it is 0 for k, an integer. And so because of that, any polynomial has a finite expansion like this, and such an expansion can be is valid also for all the entire function f of finite exponential type less than this number omega, which is the root of omega exponential omega plus 1 equal 1. And so there is a unicity of such an expansion. And so if an entire function of exponential type less than this omega vanishes at all the integers for the derivative of order n, it is a polynomial. And Françoise Bertrand-Diaz investigated the question of integer-valued entire function for this fn of n, and she proved that if the function has a type which is less than tau 0, which is the root of tau 0 exponential tau 0 equal 1, then it is a polynomial. And she proved a little bit more by taking a number tau 1, which is 0.616, which is slightly larger than tau 0. Similar to what was done before for the result of Polya by Zellberg and for the result of Carlson. So there are a lot of variation on this theme: analog, multiplicative versions, analog infinite characteristic, congruencies, and several variables. A lot of work have been done by many authors, but I would like to conclude this section survey by mentioning a problem which occurred in the work of Masser, who studied the question of integer-valued entire function over z of I, and it gave rise to the final result on gamma on the constant of Gelfond by Gramin. But when they were studying this question, they introduced a two-dimensional analog of Stirling formula. This is the limit of the sum for k equal to up to n of pi rk square minus 1 minus log n. Rk, this sequence of integers, Rk is the radius of the smallest disk in R square that contain at least k integer lattice points inside or on the boundary. The disk is not assumed to be centered at 0. If it is centered at 0, the problem is completely different. But we ask the one smallest disk in R square that contains at least k integer lattice points. We expect that pi r k square is essentially k. And so this is essentially the sum of 1 over k. And the sum for k equal to up to n of 1 over k minus log n has a limit. So it is the case for this constant gamma, delta. And this constant has been computed for the first 4 digits, but we know only 4 digits. There was a conjecture of Gramin before who succeeded with Michel Weber to compute 3 digits, and he had a conjecture with a closed form for delta involving the L function of z of I, but well, it turned out that this conjecture is not true. So this delta is very mysterious, and to compute 1 more digit is a challenge. Okay, so I would like to complete my lecture. I suppose I have something like 5 minutes or a little bit more, Kalian? Or... Okay, so I continue until you say that it's over. Okay, so I would like to discuss other problems which are related to integer-valued functions. And I will start with Lidstone. For Lidstone, we take 2 points, and we ask a condition on the derivative of even order. So you see, it's not a 2-point integer-valued function because we do not ask something on the derivatives of odd order. We ask that the values are integers, the second derivative is integer, the derivative of order 2n is an integer. And so I will explain a little bit Lidstone interpolation. And after that, I will explain that we can do something similar for another problem where you take alternatively the derivative of order 0, 1, 2, 3, 4, and so on for each point, S0, S1. Maybe I could say something to explain that if you look at Leadston, this is what I mentioned at the beginning, that I learned about Leadston at this conference on special functions. It's rather natural to, after Leadston, to look at Whittaker, you see, which is this picture here. But if you look at Whittaker, and if you, instead of taking S0, S1, if you put S1 first, then S0, then S2, then S1, S0, S1, if you put them horizontally like this, you will have the same picture as in Abel interpolation. So Whittaker and Abel have some similarity, and I will mention something which includes both Whittaker and Abel, which is Goncharov interpolation. Okay, let me start with an arithmetic result for Leadston interpolation. The result is the following. You take two complex numbers, S0, S1, which are distinct, and you take an entire function which has all the derivatives of even order at S0 and S1, which are integers. You have to assume that the exponential type is sufficiently small, and the exact value is this one, the minimum of 1 and pi divided by S0 minus S1. And the conclusion is that f is a polynomial. So I want first to explain why this is best possible. We have the minimum of 1 and pi divided by S0 minus S1. And so I have to explain why we need 1, why we need pi over S0 minus S1. So the result involves 1 and pi over S0 minus S1. If you look at the function hyperbolic sine of Z minus S1 divided by hyperbolic sine of S0 minus S1, it has exponential type 1, so it does not satisfy this condition. The values at S0 is 1, S0 minus S1, and the value as S1 is 0, is the hyperbolic sine of 0. And the second derivative of f is f. And so all the derivatives of even order at S0 are 1, and the derivative of even order at S1 are 0. So this proves that the 1 here cannot be improved. Now for the order pi over S0 minus S1, you take the function f of z, which is the sine of pi S0 minus S1 divided by S1 minus S0. All the values at S0 and S1 of the even derivatives are 0, and the exponential type is exactly the one which is here. So this explains why we cannot do better than that. I want to give a sketch of proof. And I told you that I will use the variant of Polya's result, which I mentioned before, which gives the following result. If you have an entire function such that the lim sweep of exponential minus r squared n of z0 within z minus 0 is a finite set. Okay, I have a message saying that my connection is not good, but I hope you hear me. Yes? Do you hear me?
We can hear.
Okay. So, thank you. So, the consequence is the following. If you take a function of exponential type less than 1 and two complex numbers such that all these derivatives are in z, then only finitely many of the numbers f2n of S0 and f2n of S1 are not 0. So this is where we use the fact that the exponential type is less than 1. We deduce that these values, which were assumed to be in Z, are in fact 0 values. And I explained before that when we look at the integer valued entire function, we compare with 0 values instead of integer values. And this is what we are able to do using Polya's result. So the type is less than 1. This condition is satisfied much more than this condition. And therefore, only finitely many of these numbers are not 0. And this is where we introduce Leadston polynomials. We have two sequences of complex numbers. Only finitely many of them are not 0. Leadston polynomials tell you that there is a polynomial p such that the derivative of even order at 0 is an, and the derivative of even order at 1 is bn for all n, because only finitely many of them are different from 0. And so using these Leadston polynomials and with a small change of variable you map 0 to S0 and 1 to S1, you deduce that there exists a unique polynomial such that the function f tilde equal f minus q takes derivatives of even order which are 0 at S0 and S1. So this is the first part of the proof. And for the second part of the proof, this is where you will use the fact that the exponential type is less than pi over S0 minus S1. There is a result of existence and unicity for an expansion of a function of exponential type less than pi, which has all the derivatives which are 0 at 0 and 1. I use only the unicity, which is due to Poritsky, and which state that if an entire function of exponential type less than pi has all these derivatives of even order which are 0, then it is a polynomial. So using this result, you deduce that f tilde is 0, and so f is a polynomial. So this is a brief sketch of the proof, but I will give a reference later. So we can do the same for the Whittaker interpolation. We take the derivatives of even order at S1 and the odd order at S0. And the assumption now is very similar, but it is pi divided by 2, S0 minus S1. So instead of, well, there is a 2 here, which was not there for the Lidstone extrapolation. This is best possible, and the examples are very similar to the one before. For the type 1, you take hyperbolic sine of z minus S1 divided by hyperbolic cosine of S0 minus S1. And again, it's a solution of the differential equation f double prime equal f. And for the exponential type pi over 2 S0 minus S1, you take the function cosine of pi over 2 z minus S0 divided by S1 minus S0. And so this is best possible. So we can do something else, which is instead of taking 2 points like in Lidstone, you can take 3 points or k points. And this was studied by Poritsky. And also you can take in the Goncharov-Abel situation where you take finitely many points for Goncharov, and you take for each derivative one of the points. You take, for example, f of z0, f prime of s1, f double prime of s1, f triple prime of s0, f4 of s2, and so on. So for each derivative, you take one of the values. And you see that here, if you take the sequence S0, S1, S2, Sn, and you get the Abel interpolation. So Abel interpolation, which may look a little bit bizarre at the beginning, is a special case of a general situation. So for the Poritsky interpolation, the result is the following. You have finitely many points, S0, Sn minus 1. You have a function of exponential type, which is sufficiently small. And you assume that all the derivative of order multiple of m of the Sj, the m here is the number of points, you assume that they are integers, then f is a polynomial. And for n equal 2, we have seen with the Lidstone interpolation that we get the best possible result for the assumption on the exponential type. And I am able to give the best possible exponential type, but it would take some time to explain what is the value, but we can take the best possible value. For Goncharov-Abel interpolation, I do not know the best possible result in general. So the Goncharov-Abel interpolation, the result is the following. We assume that for each sufficiently large n, one at least of the numbers fn of Sj is in Z. This corresponds to the points which I had, one for each derivative. Then f is a polynomial. And this is an open problem to know what is the best exponential type which can be reached with that. Okay, I promise to give you some references. I have 4 references. The 2 first ones are research papers. The first one is to appear in the Southeast Asian Bulletin of Mathematics. The second one already was published. The first one is for 2 points here. The second one is for finitely many points. I wrote the first paper before the second one, but it is not yet published, and the second one is published. The Moscow people were very fast. And I wrote a survey which corresponds more or less at what I explained today. And it is to appear in the proceeding of the Journée Arithmétique in Istanbul. The last reference is a course which I recorded just last week from the 7th to the 10th of December in the SIMPA in Nice. And it is a course which I am giving for the Mumbai Raman Rai Rural Autonomous College in Mumbai. And so there are 4 courses which give a lot of details on all this interpolation. And there are 4 videos on YouTube. If you want to have the link, you can look at my homepage, which is here, or then you can download this file, and then you click on this link here, and you will have the YouTube link for the 4 videos which have been recorded. The last video is very similar to the talk which I gave right now. So I thank you for your attention, and thank you again for the invitation. I enjoyed giving you this talk.
Yeah, thank you, Michel. Thank you so much. And right, so now we are in the question page. If there is any question, then we can ask. Of course, Michel is going to go back to the quiz. He's not going to leave you guys. So if there is any answer from YouTube viewers, listeners, so might be there. Otherwise, Michel has to set up. We can wait. It doesn't seem like any question here. In the seminar room, it's not there. It was so explicit, each of the things, and it was started from very basic things. So most of the things, the beginning are very clear. So it doesn't seem like Michel. So maybe you have to give us why it is not a counter example.
Yeah. Thank you again. Okay. Bye bye.
No, Michel, that quiz.
Sorry.
The quiz answer.
Excuse me?
The quiz, what you gave initially, why that was not a counter example?
Oh, I did not understand your question. The sound is not very good. Could you repeat your question?
There was a quiz in the beginning. Quiz.
The quiz. Oh, I forgot the quiz. Yes. Okay. Thank you. Thank you for reminding me. So, I expect someone has an answer to the quiz.
Yeah. So it doesn't seem like so. We can ask the viewers or the attendees maybe like to do that.
Okay. So no, I can give you the answer to the quiz if you like it.
Sure.
But I have to open again the file because I'm afraid that it disappeared. So
okay. So you need not worry again. And
okay. It's fine with me. Okay, it's fine with me. Do you see my files?
Sure.
Do you see them?
Yes.
Yeah. Okay. So integer valued functions on yes, it was on the completely. It was on completely integer valued functions. So nobody has an answer for that. It's a nice problem.
Yeah. So that's
okay. So the quiz is the following. So you see, I explained that a function which has exponential type less than log2 can strictly less than log2, a transcendental function cannot be integer valued unless it is a polynomial. And so this function is a completely integer valued function. So it is an integer valued function. And the result of polia is true. So the one assumption is not true. And the assumption which is not true is that this function is not of exponential type less than log2. You see, in the example which I took before, I took u greater than 1. So u minus 1, the logarithm of u and the logarithm of u minus 1, log u minus 1 is minus log u. But here, this is in fact why I have taken plus 1 here, in such a way that the two numbers are positive. But here, when you take the golden ratio, the number phi tilde is a negative number. And when you write phi tilde to the n, it is well defined. But if you look at phi tilde to the z, it is exponential z logarithm of phi tilde. It is not logarithm of modulus of phi tilde. It is logarithm of phi tilde. And so you have to choose a logarithm of phi tilde. And phi tilde is a negative number. So the logarithm of a negative number is the logarithm of the absolute value plus or minus I pi. And so when you look at the growth order of phi tilde to dz, it is not log of phi tilde which is important. It is the modulus of the log of phi tilde that you choose, of the logarithm of the negative number. And so this logarithm is greater than log 2. So this function grows like exponential the absolute value of the modulus of log of phi tilde. And it grows faster than log 2 times z. Okay, so this is the answer to the quiz.
Thank you so much, Michel. So let's thank Professor Michel Waldschmidt once more for his wonderful talk. And not only Michel today, let's give a big thanks to all the speakers who really was with us today. So thank you to all, thanks to all of you, all the speakers. So that's the end of Michel. Have a Merry Christmas and fantastic year ending.
Okay, so I stay here. Yeah. Okay.
No, Michel, I'm saying that we are just thanking all the speakers.
Oh, yes.
I'm telling you Merry Christmas.
Okay, Merry Christmas. Okay, thank you very much. I enjoyed to be with you. I would have preferred